Kia ora everyone. As you go through the TGC derived grade exam for Level 3 Chem 2024, and this is the bonding and thermochem paper. All right, we're starting off with a lovely question on Lewis structures. So we've got our P in the middle and all of our halogens are arranged nicely around the outside. Love it when you get lots of halogens because they're all the same. So we need to make sure we've got 7 electrons drawn in pairs and they're all single bonded. And 1, 2, 3, 4, 5, 6. 1, 2, sorry, these are a bit crooked because I'm trying to hold my phone here. And so there's 5 areas all bonded. So that is trigonal bipyramid. Most of you got that one. Some of you forgot to draw the non-bonding electrons. This one we've got an I in the center and we've got 4 F's around the outside. So let's just start with those F's around the outside because they're halogens and that makes it nice and easy for us. Okay, so there's my fluorines all done, and so now I have to get my iodine sorted. So it is also a halogen, so it's got 7 valence electrons plus this one here, so it needs to have 8. So we've got 1, 2, 3, 4, 5, 6, 7, 8, and we do need to show that we've got an extra electron from somewhere else. That's now got 6 areas with 2 non-bonded, making it a square pyramid. And that was a bit of an easy merit, which helped some of you, so well done if you got that. This tricky thing here is only tricky because if you just take the diagram, you're going to think it's bent, and it's really not bent. And actually some of you even contradicted yourselves, so just try and keep your thinking as clear as you can. So we have got, there are 5, 1, 2, 3, 4, 5 areas of electron density around the central atom. Most of us got that. These areas, this is our link here. So I want you to link the total areas to the repulsion in the parent shape. So these areas, the best way to say it, occupy positions to minimize repulsion. Somebody far cleverer than me said that was the best way to do it, and this person is one of our chief chemistry markers, so that's the way I do it. In a trigonal bipyramid arrangement. Some of you put the bond angles in, you didn't need to do that. Okay, so that is a link. We are linking the total areas of electron density to the parent shape. Then we are going to link, in fact, I'm just going to go back a sec because some of you still want to say these areas repel and then minimize repulsion. And that same clever person told me this was it was a bit of a clunky way to say things. The areas don't get there and then repel. They just occupy the positions to minimize the repulsion. It's just the way it happens. So this is the best way to say it. So try and say it like that. There are 2 bonded and 3 non-bonded areas, and we're going to link this to the molecular shape. Therefore, the molecular shape is linear. Now, if you put bent here, the maximum you can get is merit because you're going to get the wrong polarity, unfortunately. Right, now that we've done the shape, we're going to cut to the bonds. So we're going to say the XEF bonds are polar, and we're going to say why? Because XE and F have different electronegativities. You could say that F is more electronegative than XE, but you don't have to. We should know that because F is the most electronegative element. Then we would say this means, now this is kind of an added extra, but I quite like it. This means the electrons are shared unevenly in the covalent bonds and bond dipoles form. Then we need to say, as the shape is linear, so we're linking back to the shape, as the shape is linear, the bond dipoles, or the dipoles, are arranged symmetrically therefore the dipoles cancel. There's other ways you can say this. You can say the centres of positive and negative charge coincide, and XeF2 is a non-polar molecule. So hopefully some of you will learn something from that. Over here, some of you skipped this, but it kind of is important to get this for the following questions. So sulfur's number 16, gallium 31, selenium 34. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p4. So that's 2, 8, 6, adding up. So you can see how doing it like this is the first main energy level, this is the second, and this is the third. That is going to be useful for us when we come down here. And some of you, because you do this in a bit of a weird order, you kind of aren't making that link down here. Right, so gallium 31, some of you started with the closest noble gas, which I think was xenon, but I'm just going to do the whole lot here for you. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4s1. Notice how I did the 4s2 first, but I left space for the 3d. That's because I do like to remind myself how many shells this have and which is the valence shell, which is the 4s shell. So that's why we tend to like to draw this here. Sorry, that should be a 4p. We tend to like to draw this out here because these are the ones that are going to be lost first. When you hide it in there, you tend to get that wrong at times. 34 is going to be the same as 31 with 3 extra electrons. So 4s2 and 4p4. And then Ga2 plus is the same as Ga, but we're going to remove 1 electron from 4p and 1 electron from 4s. Some of you did remove it from the 3d because you put the 4s in there. So Ga should be like this. Okay, and you needed to get 3 of those for the achieved. Luckily, most of you got these first 3, so that was good. All right, so the order, I probably would have left the order to last, so let's just have a look at what we've got here. Just remember to read carefully. Some of you didn't use these 3. It was a bit silly. So we've got S and Se, and if we look on the periodic table, which I'll just grab now, the periodic table, S and Se here. Here is my sulfur there, and here's my selenium. So these two are in the same group. So we're obviously doing a group comparison here. And Se2 plus, 2 minus is just an ion atom comparison. So I'm going to compare these two, and then I'm going to compare these two. All right, so S and Se are in the same group. Please make sure you get your groups and your periods right. S has 16 protons, and I'd write that properly. I'm just doing this for this video, and 3 shells. So I can look back up here and I can check my 3 shells. Whereas Se has 34 protons and 4 shells. 1, 2, 3, 4. Okay, so despite having more protons and therefore a stronger nuclear charge, Se has 4 shells. This means there is more shielding than an S. I'll just drop that in there, and which is inner shell electron repulsion, and therefore the attraction between the nucleus and the valence electrons is less in Se due to the extra shell. Therefore, the distance from the nucleus to the valence electron is greater in Se than S. Okay, so I know Se is greater than S. Okay, Se2 minus and Se have the same number of protons, 34. I'm pleased not too many of you put that protons were gained, and the same shielding effect. Some of you got this a bit wrong. They have the same number of inner shells. However, Se2 minus has 2 extra valence electrons. Some of you got this number a bit wrong. Should be 6 and 8. 2 extra valence electrons, therefore increased valence shell electron-electron repulsion. Therefore, the atomic radius of Se2 minus is greater than Se. Now notice I didn't put anything like atomic radius increases down a group or atomic radius is bigger in the anion compared to the atom which it was formed. Those kind of things that you memorize don't tend to get you many points. In fact, you could have got some points just from getting the order right. So S is smaller than Se and Se is smaller than Se2 minus. So that is my order there. So I'm just going to do that at the end just because then I can go through my reasoning first and make sure that my order is correct. Over the page, we've still got some more periodic trends here. So the first ionization energy of selenium, so that is selenium gas going to selenium plus gas plus an electron. And down here, we needed to circle one. A couple of you forgot to circle. Size of the first ionization energy of selenium compared to gallium. So if we get back our trusty periodic table, we can see that selenium is here and gallium is here. So we're comparing two that are going across a period. So that's our comparison here. It's an across a period comparison. So we would go Se and Ga are in the same period, therefore have the same number of electron shells and shielding, which I'll just remind you is inner shell electron-electron repulsion. However, selenium has 34 protons, which gives it a stronger nuclear charge than gallium, which has 31 protons. Therefore, the attraction between the nucleus and valence electrons is greater in Se than Ga. This means it takes more energy to remove the least tightly held electron. Doesn't mean it's loose or not tight, but it's the least tightly held electron from a mole of gaseous, more energy from selenium than from gallium. And that's why our ionization energy is higher. So that was actually a numeric question because you're only doing one comparison. So your two excellence parts were this part and this part. So if you missed out this, if you put your bent, that really did affect you quite a bit in question 1. Okay, let's go into question 2. Right, so it was really obvious that some of you hadn't learnt your definitions. So vaporization is when you take the substance in its liquid form and you turn it into its gas form. And fusion is when you take the substance in its solid form and change it into its liquid form. And you needed to know that to say, why is this one bigger than this one? Right, so we're going liquid to gas, so that is our boiling point, and solid to liquid, which is our melting point. So this question was asking, do you know what happens when we melt compared to when we boil? Right, so the delta fuse is the energy required to melt 1 mole of a substance by loosening the forces between particles, and we know what they are. And I'm actually going to go back, loosening, and I'm going to put / breaking some of the forces between particles. In this case, with between C6H6 molecules, whereas the vaporization is the energy required, sorry about my messy writing, energy required to completely separate all C6H6 molecules in turning 1 mole from liquid to gas. Therefore, more energy is required to break all bonds than some bonds. Right, so that's what we were after there. This one here is your heating curve. So why heating initially results in an increase in temperature, but once it begins to boil, the temperature remains constant. So I was really pleased to see some of you do that. That is what you needed to do. So we need to talk about 1. So this part of the curve here is when the temperature is increasing. So that's our temperature there. And you needed to define temperature. Temperature equals the average kinetic energy of the particles. So when heating liquid, the kinetic energy of C6H6 molecules in this case increases, therefore the temperature increases because I've defined temperature. However, once the boiling point is reached, the heat energy is used to break the width between C6H6 molecules. So no increase in EK occurs, right? So they're not speeding up at this point. Therefore, the temperature remains constant. So remains constant. The biggest thing you had to do here was this definition. This is why your definitions are important, because if you don't know that temperature is average kinetic energy of the particles, then you can't get enough specificity in here. So these were M each, but if you did them both well, you got a combined E. So some of you got 2 M's, and 2 M's isn't the same as an E. An M could be a reasonably good answer, but both of them had to be really good to get that E. So well done if you got that. Over here, this is our first calculation, and if we notice, all of these are enthalpies of formation. And most of you realise that the enthalpy change was going to equal the products minus the reactants if you have all enthalpies of formation. However, what you forgot was that this side is the products, and this side is the reactants. So when you use this method, just notice that you cross these over, because a lot of you got this wrong. And some of you were very, very sloppy with your with your signs, and if you got your signs wrong, then that flowed on to the next question, unfortunately. So these are really important. So my products are sodium carbonate, so that is negative 957, plus water, which is negative 285, plus carbon dioxide, negative 394, minus my reactants, which is 2 times... Oh, I've done that wrong, haven't I? Made a mistake. Good, I noticed that. So I'm going to go back here. My product is a sodium carbonate, so that's 1131. And so my reactant is the negative 957 times 2, because I've got 2 moles of it there. So if I do the maths of that correctly, I get plus 104 kilojoules per mole. So it actually is only a merit question because it's not that hard. But a lot of you just rushed that a little bit. You either didn't do this or you didn't minus a negative, which is going to be a adding in the end. So just take care on that, because now we need to do our entropy question. So we need to have our total entropy equals our entropy of the system plus our entropy of the surroundings. So I'm going to start with my entropy of the surroundings, and I need to say, as delta H is positive, the reaction is endothermic. Now just remember, for surroundings, you've only got 2 answers. You've got an answer for an endothermic reaction and an answer for an exothermic reaction. So this is my endothermic reaction. I've got energy is absorbed from the surroundings, and we need to say what that means. Therefore, the surrounding particles slow down, decrease energy, become more ordered. And you can also say that there is less dispersal of matter and energy, which I know a lot of you like to say, which is great. And this means that the entropy of the surroundings is negative, not favoured. Okay, in terms of the entropy of the system, we have got up here, we've got 2 moles of solid going to 3 moles of solid, liquid and gas. So we've got an increase in both the number of moles and in the disorder of the states. But you can't say there's a state change because it's a chemical reaction. It's not just a state change. So we have to say there are 2 moles of solid reactant, which react to form less ordered products, 3 moles, and solid, liquid and gas. Therefore, the entropy of the system is increasing, which is more disordered, which is favoured. So we've got a positive entropy of the system and a negative entropy of the surroundings. Actually, a couple of you did say decreasing and increasing. I'm just not quite sure that's the best way to say it. So let's just talk about positive and negative here. So then we would say that as the process is spontaneous, the total entropy must be above 0. And then we need to say, and most of you got this, that the positive entropy of the system must be greater than the negative entropy of the surroundings so that the total entropy is positive. So that's another excellence question there. Most of us did okay here. A couple of you could probably put in a little bit of effort and do, kind of get another merit or excellence here. And on to the last question. So this, nobody really got this one. Explain why the enthalpy change is classified as an enthalpy of formation. You needed to know the definition of enthalpy of formation is that 1 mole of, in this case, ZnSO4 is synthesized or produced from its elements in their standard states. That's all you really needed to say then. I'm just going to change my pencil. Okay, this one was a tricky one, and there was a couple of ways that you could have done this. And most of you did okay with this. I do encourage you to leave your working there, even if you don't think the answer's right, because those of you that did that managed to get some points. Those of you that rubbed it out obviously didn't get any points. So the first thing is we need to determine this enthalpy of formation, which is this reaction up here. So I'm going to start with that. This is what I want, plus SS plus 2O2 gas goes to ZnSO4S. That's what I want. All right, I'm going to put a line underneath that, and I'm just going to make sure that I line everything up there. Okay, so using these, this is a Hess's law question. I can either use these equations to get what I need or to cancel out what I don't need. So I'm going to start with the zinc sulfate, which is in this one here, because I want 1 mole as a product. So I'm going to keep this one here as is. ZnO plus SO3 goes to ZnSO4 solid, right? So I kept that the same, so that's minus 230.3. And actually, I've just noticed something with the significant figures there. There's 4, isn't there? I might go back and change something there. Okay, so in that case, I've got my ZnSO4, so I want that. Those two I don't want, so I'm going to try and cancel them. All right, so I could try and cancel my ZnO now. So to cancel my ZnO, I need, here is the only other place I can find it. So I'm going to reverse this, and I'm going to halve it. All right, so I'm going to put them the other way around. So that's going to give me 2ZnS solid plus 3O2 gas goes to 2SO2 gas plus, sorry, I'm halving it, so let me take that down. That's going to be ZnS. That's going to be 1.5 O2, and it's going to be one of those, plus ZnOS. So reverse and half that. So I'm going to, that's going to be a negative now, and a half of that. 927.5 divided by 2 equals, it's going to be negative 463.75, and now I have cancelled my ZnO. It's an SO2, and I've got nothing else there, so I've still got to either use these or cancel them. So I've used that one and I've used that one. So let's see what I'm going to do with this one here, maybe. So what do I want to do with that? I probably want to get rid of my SO3. So I need to, I need to keep it on the same side, but I need to half it. So that's going to give me SO2 plus half O2 goes to SO3, and I'm going to half that. So that's negative 196 divided by 2, so that's negative 98. And let's see what that does here. So I've got SO3, which I can cancel, and I've also got SO2, which I can cancel. And look, I've got 1.5 plus a half, so that gives me the 2O2 I want. So I've now got that, and I've got that. Right, and this is the only one I haven't used, so it's the right way, and I need to cancel out that, so I leave it as it is. Sorry, it's interval. It's all the squealing behind me. Plus SS goes to ZnSS, leaving it as it is, minus 183.9. That's going to cancel out my ZnS, and it's going to leave me my zinc. So all I've got left is zinc, sulfur, 2 oxygens, and ZnSO4, and when I calculate that all together, it should give me my answer. Right, and that gives me 975.95, which is 976 kilojoules per mole. All right, and of course that's a negative. I want that in 3 sig figs, but I'm actually just going to check. If it was 976 if it was 4 sig figs, it would be 976.0. So since they gave you the values in 4, which they wouldn't do in NCA, I'm going to accept the answer in 4, so I might go back and have a look at those. Okay, last page. So here we've got our WIF question. So HF, we've got hydrogen bonds. It's therefore polar, so it's got PD, PD. and everything has TD. So just a note here that hydrogen fluoride is polar. So it has a permanent dipole. This thing here is a permanent dipole. That is a permanent dipole. The attraction that we are looking at is the attraction between two permanent dipoles. Right, so that's why we write PD, because it's this attraction here, the attraction between two permanent dipoles. So that's just explaining why that's important. Each molecule forms a permanent dipole. The interaction between them is two permanent dipoles interacting. This thing here is polar, so it's PD and TD. And this thing here is non-polar, so it's just TD. Now, I did cut you down for not writing this out in full at least once, because they will do that in the end of your exam. So please make sure you write it out in full in this box, and then you can use the abbreviations from there. All right, so we're looking at why is this lower than both of these. So essentially, we're just explaining all three. And actually, probably there were so many different ways of explaining it, but I like the way that for this question that started with the TD. All three molecules form TD between molecules. The strength of this is related to the molar mass. Okay, and we can just get that out of the way here. So if we look at our molar masses, Cl2 has the largest molar mass, therefore the largest electron cloud, and the strongest TD. So what I don't want you guys to say is that TD is the weakest form, because in this question it's not. So there's no point saying that, and it's just a little bit annoying. So just talk about what you've got here. In this case, chlorine has the largest molar mass, therefore the largest electron cloud and the strongest TD forces, followed by chlorine monofluoride and then hydrogen fluoride. Right, and then we've addressed the size of the temporary dipoles right from the start. Okay, so we've said why chlorine's got the strongest temporary dipoles. So now we need to make a couple of individual comparisons. So we could then say HF still has the highest boiling point, as it forms all three types of whiff. So despite having the weakest temporary dipole, H bonds form between molecules as F is covalently bonded to H, therefore a very strong dipole forms and means a strong interaction, or attraction is probably better, attraction between molecules. So that's really important. HF is polar, therefore forms PD. You don't need to go into detail about polarity. It adds nothing. Why it's polar. Okay, the sum of attractive forces is probably the best way to put this. Forces is greatest in HF, therefore has the highest boiling point. Okay, so we've got that highest one. ClF is polar, therefore forms PD. However, this is not enough to overcome the effect of molar mass on TD in this case, because look at those boiling points. Therefore, although chlorine only forms TD, the strength of this is greater than CLF's PD and TD. So CLF has the lowest boiling point. And you probably should put in and needs the least energy to separate the molecules completely, turning liquid to gas, something like that. Okay, so there was quite a wide variety in your answers, and some of you lacked a bit of detail, reasoning and clarity. So have a go at that, and hopefully you can make some improvements in that, some of you. All right, last question. Okay, we struggled with this, but the biggest place we struggled was this. You wanted to use N equals M over M. You do have a mass, but it's the mass of a mixture. So that there is going to be used in the Q equals MC delta T part. Right, to find the number of moles, remember you've also got this, N equals CV, and you do have a volume and a concentration, and another volume and another concentration. The next issue, if you chose this, was which volume and concentration to use. If you try and use them both, you will find that if you do volume times concentration for each of these, you will get the same number of moles. So let's just use one of them. So 0.2 litres times 0.3 moles per litre equals 0.06 moles. You do not add moles together. The same number of moles is reacting for each of those. We never add those together when we're doing calculations, especially those of you who've done aqueous are probably going to get this a bit easier, I think. Anyway, that's a good lesson. So if the moles were different, you'd use the lowest one, but they're probably not going to be. They're probably just going to be the same, and they're just testing if you know to use any one of them. So that's our number of moles now. Some of you also wanted to use this, that the delta H equals a negative Q over the N. I don't like using that. I don't like using the negatives because that really stuffed a lot of you up. So I tend to not use any negatives and just think. I know that the delta H negative is the only important thing because that means it's exothermic, and I know that the temperature is therefore going to rise. That's all I need to know about my negatives. So I'm now going to use this. So I've got 0.06 moles, and I know that 56.3 kilojoules per 1 mole. So I actually want to go 56.3 kilojoules per mole times 0.06 moles, and that's going to give me the amount of kilojoules that I'm actually going to use. So 56.3 times 0.06, that gives you 3.378. But if you use your units like I've just done, you'll realise that that's kilojoules. And when we're coming backwards, we're going into the Q equals MC delta T, we need to turn that into joules. So we times by 1,000 to give us 3.378 joules. And from that point, those were probably the two tricky bits. Then we've got 3.378 joules equals the mass of the mixture, 300 grams, times 4.18 times the change in temperature. So we rearrange and solve for that change in temperature. So I'm just going to do that here. And that gives me 2.69 degrees. And because I understand that exothermic temperature would rise, I'm going to go 25. My starting temperature plus 2.69 equals 27.69 degrees, which equals 27.7 degrees. And that's my answer. And that's the end of interval. And that's the end of this very long video.